Hi everyone, going to go ahead and continue on talking about light as a wave. And last time what we said is we have different properties that waves have. We talk about wavelength, the size of one wave. We talked about frequency, the number of those waves that pass by per second. We talked about wave speed, how fast the wave is traveling through space. And we said that there was a relationship between those three. That wave speed is equal to wavelength times frequency, referred to Light1 for that. And then we said the wave size is given by amplitude, which is measured from the middle of the wave up to the crest, or the middle of the wave down to the trough. They should be the same for these type of waves. And as we talk about waves, there are some properties that waves have that particles don't have. One is this ability that waves have to bend around barriers. And so what that is, to bend around a barrier, is known as diffraction. And that again, waves can bend around barriers. So remember, if there's in the classroom and you're over here and the door's over there, you can't see someone in the hallway, but yeah, you can go ahead and hear them. In other words, as some person talks, the sound waves travel and they can bend around so that you can actually hear them even though you can't see them because they're hidden by the barrier of the wall and they only pass through the doorway. Think about this. If this person tossed a ball there, you couldn't make it there unless, of course, it bounced, but that's not what diffraction is. Diffraction is where it literally doesn't reflect off the wall to you, but what it is that sound waves or any type of wave can bend around a barrier and actually reach someone that's not even where they can see the source of the type of wave, in this case, sound. So no particle can do that. Particles don't come along and then zip around a barrier to find you. But sound waves can, and it turns out that light waves can. And so diffraction is the bending of light around a barrier. And again, what we had was this. You see waves coming in toward the shore. We have this barrier right there. And as they pass, as the waves come through here, they're bent around so you can actually find wave motion behind the barrier. No particles could bend around to come over there. So that's one type of wave behavior that particles don't have, the bending around a barrier called diffraction. Now, there's another type of wave behavior, and it's called interference. And it turns out that this is how waves can add together as they pass through space at the same time. So if I have a wave passing this way and a wave passing this way, where they're crossing, where they're meeting up, they can actually add in particular ways. So let me be very precise about it. There's at least more precise than this. Let's imagine that you have a wave here, and so this is wave 1, and it's traveling in that direction, some speed v. Here's another wave right here, and that's traveling speed v. They can add, and notice the crest is lined up with the crest, the trough is lined up with the trough, and so forth. And what I can get is actually a bigger wave than the waves that make this resultant wave up. So this is known as constructive interference. constructed. They're adding to make two or more waves can add together to make a resultant wave bigger than any of the individual waves that actually added up together. And so that's one type of action. Now, if I mentioned before, if I toss a particle and smack you in the head with this, which I won't, if I throw two, well, maybe twice as much pain. Silly, right? And that seems to be like this, but it really isn't. So let me give an example. We have constructive interference, but there's another type of way that waves can add together. And let me show you. The previous, for constructive, as the waves pass by a certain spot in space at the same time, the troughs and the crests lined up to get that additional size of the wave. But if I have a wave that's traveling through space like this, but now the wave's lined up like this, notice now the crest lines up with the trough, and the trough lines up with the crest, and when they add up passing through space, I can get hardly any wave action. And so this is known as destructive interference. No way could two pins be tossed anywhere in space and have them add up to zero. So particles could never behave that way. And so one place where that could be utilized are those those headsets that are sound suppression headsets. So if you have sound that can be picked up by electronics surrounding you, then the electronics can produce a second wave that would basically interfere with that external sound to produce hardly any sound. And so that's possibly one way that you might see this. I always tell the story about the early 90s. There was that large earthquake centered in Northridge, and it happened that night. My daughter went to Northridge to stay with some friends, and so of course that was quite a concern. So the next day, as I went up there, I took a neighbor who apparently his parents lived just a few blocks from where my daughter was. Now it's just like today, as we're going up the 405 toward Northridge from the basin of Los Angeles, there's hardly anyone on the freeway and on the 405, kind of like how it is now. We've had these weird times before. And so when we got off the freeway and I dropped off my neighbor, it was pretty terrifying. He had 2x4s broken in his parents' home, and the garage door was laying on the ground, and their home was quite a mess. So I got very concerned for my 6-year-old daughter being at this friend's house only a few blocks away. So when we got there, it was a pretty astounding thing to see. What I saw was nothing wrong with this home at all. Talking to our friends, they said the only thing that happened is a glass was on a counter and it bounced off the counter and fell on the floor. See, what was happening is the earthquake waves were rising up from the ground, and they were hitting the mountains, the Santa Monica range, and as the waves rose up, this reflected, and so you had two waves passing through, the normal earthquake and the reflected earthquake waves. And where my neighbor's folks were is where those earthquake waves lined up so that there was constructive interference. So the ground shook a lot more than what maybe normally would be found. Whereas at my daughter's location, the waves interfered in a destructive manner, so the ground motion was much less. Just a kind of astounding physical demonstration about how waves work. Now, remember what we said, that at first Newton felt that waves were a particle he called corpuscles, but Young came along and he did what's known as Young's diffraction experiment, and he showed that light was a wave. And what that was this. You had a barrier, and in that barrier, basically two small openings. And so they're called a double slit. Two small openings. And there was a screen back over here. And he illuminated this with light. So this is light that would illuminate. And it turns out that the light waves bent around the barrier and traveled outward from the 2 points. And what he got is a region that's behind the screen, behind the barrier. It was very bright, and then very dim, and bright, and then dim, and bright, and so forth. So again, dim and bright, and dim and bright, and dim and bright. And so you got this alternating pattern of very bright regions behind the barrier with the two small openings, and some, some light areas and some dim areas. And these areas where there was constructive interference, because the waves are interfering at the screen as they would pass from the two slits, as you can see. And that meant that where it was constructive is that the waves emanating from both slit 1 and 2 were lined up together, crest to crest and trough to trough, so they would add together. But in these regions where we have destructive interference, the waves lined up in a manner that the crest was with the trough and so forth, and so they would destructively interfere. So we get, with light waves, two wave properties, not particle properties, both diffraction and interference. So this very, very famous experiment run by Young really demonstrated that light had to be a wave, And so that was an amazing discovery, totally amazing discovery. And that certainly did show that it seemed that Newton was incorrect, even though he was the famous, brilliant man that he was, and that Young showed without a doubt that light was a wave. And so when we look at waves, we have to bring in energy. And so let's talk about energy for a little bit, and then we'll relate it back to waves. And so we have to speak about energy. So I'll call this an aside. One of my little going away from the lecture we have to talk about something important, and is called energy. Now we all use the word energy in everyday life. It's like, oh, Michael, I have no energy to read today. Or here's Michael saying, well, I have no energy to talk today. That never happens, you probably know. And remember, there's no point too small I won't talk a long time about. So you know that by now. But the point here, potentially, that's how we use this. Of course, that's a subjective term. We have a much more definitive idea about this in the physical sciences. And energy is abstract, but it relates to this. Energy is related to the physical state of an object. And so when I say to a physical state, what I mean by that, it means their shape, their temperature, their location, their motion. And when I say motion, I mean, their speed and direction of motion. And so those are some of the things it's related to. And there's other items that we can bring in here, but I'll leave it simply to that. And so if there is a change in energy, if there is a change in energy of an object, and what that basically means is that the physical state of that object changes too. So what do I mean by that? It means, well, if the energy changes for an object, it means either shape changes or its temperature changes, or its location might change, or its motion might change. It might slow down, it might speed up, it might change direction and motion. So this is an extremely important type of physical quantity that we measure in the sciences. And this is especially true in astronomy, because it turns out that as we discuss the birth and formation of a star, energy is paramount in trying to understand what is taking place. But there's also something else that we have already seen. We saw that energy is formed in the core of a star. And of course, that energy that flows through the star, and we said it flows in different ways, it's called energy transport. And the radiation zone we talked about, which is in the form of light radiation traveling through that region, or the convection zone where hot stuff is rising and falling, carrying the energy. And then again, light radiation traveling out into the solar system makes life possible as it warms the Earth. Without the energy of the sun, life could not exist on the Earth. Popsicle toes, guys, there. So what we have to do then, and the way that we deal with this is we show that there's different types of energy. So it turns out that there's different types of different forms of energy. And we won't go into a huge amount of detail. There's a couple that we have to worry about in our discussions. So let me go ahead and let you make sure you have a few moments with this. Again, you can pause the video, write this out in your notes, and then we'll proceed. So I'm going to go ahead and erase this, and we're going to talk about the different types of energy that we'll probably will encounter. Not even probably, we will definitely encounter in our lectures as we go through Unit 2. And so the first one is energy of motion. So with energy of motion, here is an object of mass m. So it's made from atoms as an example, and it's moving with some speed v. So m is the mass of this object, v is its speed. And so the energy of motion is known as kinetic energy. And we define kinetic energy to be 1/2 times the mass of the object times the speed of the object squared. And so if that energy of motion is given, if it changes, then remember something happens to the object. I always tell you guys, be slow when you drive down the freeway, especially now when you could probably punch it because there's no one on the freeway. Slow down because you have a large amount of mass. You're moving very quickly with speed v. That means your kinetic energy is great. So if you hit something, that energy will change. It can't just disappear. It goes to other types of changes to the system. So your shape might change, meaning you might break a bone. Certainly the shape of your car will change as you hit something because it will deform the metal of the car. So that's one type of energy, kinetic energy. Another type of energy, so that's one. Another type of energy, two, is the energy related to how hot something is, and this is known as thermal energy. And there's a lot of details that can be brought into this. We'll keep it very simple for this particular type of class, basic astronomy, GE astronomy. All I really want to say here is that thermal energy is related to the temperature of an object. The greater the thermal energy, the greater the temperature. The smaller the thermal energy, the smaller the temperature of the object. And so we keep that in mind. Now there's another type, a third type, and it's kind of an abstract type, even though everything's kind of abstract with this. And so the idea of this is kind of like a savings account in a bank. If you put money into your savings account, you can store that up and eventually use it to do something with that money that's stored. You can buy things, you can use it to purchase different items, and according to how expensive the item is, the more of that bank account you have to use. Of course, the more you put in the bank account, the more of a savings you have, and that means the more things can be saved. Let me erase these two, and this will be a third type, and we'll need especially all three of these types of energy when we discuss the birth of a star. And this one here is known as potential energy. And in this case, it's the potential energy due to gravity. And so it's like this. Let's say I'm on a building, and the building is some height above the ground. And here I somehow climbed up to the top, and I'm just standing there. First off, I'm not moving, so what's my kinetic energy? Remember, my kinetic energy is 1/2 times my mass times my speed squared. My speed is 0, so at the top, the kinetic energy is 0. But it turns out that the potential energy of gravity is not 0. It turns out that is equal to my mass times something called the acceleration of gravity times my height. And just so you know, the acceleration of gravity, little g, is how my speed changes every second if I'm actually going to, say, drop off of a ledge or a building. And it turns out to have a number of 9.8 meters per second squared. That's the unit of acceleration. This is known as the acceleration of gravity. And all this means is that if I start out with a speed of 0 at time 0, as I just step off of a building, so this is time, and this is my speed. If at time 0 my speed is 0, after 1 second being on Earth, my speed will now be 9.8 meters per second. After 2 seconds, my speed would be 19.6 meters per second. In other words, what this says is every second I fall, my speed changes and increases by 9.8 meters per second, barring any interference from air and such. So that's what that means. So we know the value of g. You have to be given the value of m and whatever height is. Again, do you do much calculations in this particular GE course in astronomy? No. What it is trying to understand what these principles represent. Now, let's say I step off the building. Of course I won't. As I step off, I may drop down to here. And so here I am going down. And at this point, what happens, I'm going to actually take this off. And now at some height h1 here above the ground. h1 is less than where I was. And of course, I'm moving here. And so it turns out that my energy here is going to be a combination. It's going to be equal to 1/2 times my mass times the speed I have at position 1 squared plus mg in my height at position 1. So there's a combination there. At the top, the total energy I have was the potential energy because I'm not moving. Here, my total energy is a combination. Now, I continue dropping, my speed continues to change. Really, what I'm doing is, like the bank account, I have at the top here a saved amount of energy, so to speak, in my energy bank account, and it's equal to mgh. As I step off, I start spending some of that saved energy, and I spend it for kinetic energy. Now, because I've spent some of the potential energy due to gravity from the top, this one will be less than that because whatever is that's less than must go into there. Now at the bottom, right at the instant before I hit the ground, we can say my height is 0 at the bottom. Therefore, my energy total here at the bottom, this is at the top, is going to be simply 1/2 my mass times my maximum speed squared. Because the height is 0, my potential energy of gravity will be 0 because it's mg times 0. So that means all the energy has been that I saved in my bank account, equal to that, has been spent to buy this maximum amount of kinetic energy of motion. So let's recoup this a little bit and kind of go back and say this. I start out with a total energy at the top, and the energy is equal to the potential energy due to gravity. I'm not moving, and therefore kinetic energy is 0. Now at the bottom, what that means is my total energy is this right here. Height is the maximum height I'm at. In between, I spend some of that energy that I've saved in my potential energy of gravity, and it's converted into kinetic energy. So I have a combination of both kinetic energy and potential energy. At the bottom, right before I touch down, what happens is there's no longer any saved energy. It's all been spent for the kinetic energy of me falling through space. And because I've spent it all, my speed is the maximum that I could go. And the amazing thing is, if I did my bookkeeping right, the energy at the top will equal the energy in the middle, which is equal to the energy at the bottom. And so we have basically a constancy of energy, barring any external ways that energy could be lost. Now, what happens when I hit the ground? Well, sad, right? But I'm no longer moving. I'm just laying there. Where did that energy go to? And so the answer is that if you would measure the temperature of my body before the collision to the ground and measure my energy after my temperature after I hit the ground, the temperature I have in the ground beneath me after the collision will be higher than before the collision of me to the ground. Meaning that all that energy that we got originally from the potential energy converted totally to the kinetic energy, then is converted again into thermal energy. So this implies something very important about energy. And this is one of the reasons why it's so extremely important. And what that is that energy is one of those properties of nature that maintains a constancy even though it can change different forms. And that leads to one of the most important principles of physics. Let me go ahead and erase this. Take your time, walk through this. And what this principle is what's known as the conservation of energy. What that says is that energy cannot be made or created or destroyed. but can change from one form to another. Can change from one form to another. And so that's what we really showed when dropping from the rooftop. That I start out with total energy that I have, which is potential energy due to gravity, mgh. As I drop down, then my energy is converted from not being totally potential energy, but a combination of potential energy of gravity and kinetic energy, where the potential energy reduced, that energy would be equal to the kinetic energy formed, how fast I'm moving, in 1/2 mv squared. When I fall down to the bottom, all the potential energy of gravity is then converted to all kinetic energy. But the amounts at every point, at the top, the middle, and at the bottom, all are equal. I have not lost any energy. And then once I hit the ground, again, the energy is not lost. It's just converted to a different type of energy. And so in that little case of dropping off the building, that's a little system that we're working with, me at the top, dropping down. And so we can treat little systems like that with energy. But understand, this is a more basic principle. If I think about all the energy present at the very origin of the universe, in this primeval seed that the universe formed out of and expanded in, if I could measure all the energy in that tiny, tiny location, that little singularity we call it, and then I would look at the present day huge universe we have, and I could add up all the energies present in the universe, including the equivalent energy that all matter has. E, the energy equivalent, equals the mass in the universe times the speed of light squared, mc squared. If I added up everything, those energies would be the same, because energy cannot be created or destroyed. Whatever was there is still there, but perhaps in different forms. And so where do we go from here? Well, now that we have this, let's think about the energy of a wave. And so the next lecture is going to show why light has a problem with energy. It's related back to the fact that we think light is only a wave, and it turns out that the energy of a wave is related to the amplitude. And we'll talk about that, and where Einstein showed that there needed to be a new way to think about light, because light behaves differently than most waves. Okay, guys, I hope this makes sense. I hope you're doing well. Keep reading, keep working. I'll soon have another lecture posted for you. We'll continue working through light. Talk with you soon.